Problem A3. A ship can be thought of as a symmetric arrangement of soft iron. In the presence of an external magnetic field, the soft iron will become magnetized, creating a second, weaker magnetic field. We want to examine the effect of a ship's field on the ship's compass, which will be located in the middle of the ship. Let the strength of the Earth's magnetic field near the ship be BE, and the orientation of the field be horizontal, pointing directly toward true north. The Earth's magnetic field BE will magnetize the ship, which will then create a second magnetic field BS in the vicinity of the ship's compass given by this formula, where KB and KS are positive constants. Theta is the angle between the heading of the ship and the magnetic north, measured clockwise. Chords B and S are unit vectors pointing in toward the direction of the ship, bow and directly right of the forward direction, starboard respectively. Because of the ship's magnetic field, the ship's compass will no longer necessarily point north. Question A. Derive an expression for the deviation of the compass delta theta from north as a function of KB, KS and theta. Question B. Assuming that KB and KS are both much smaller than 1, at what headings theta will the deviation delta theta be largest? Solutions. To answer the question A, we need to represent in this formula vectors B and S in regular coordinates. Let's X be east direction and Y be north direction. In that case, we have B ort equal this expression and S ort be this expression. Now we can insert them in this expression for vector BS and find what are projections of this vector. In X direction we have Bx equal this expression, and in Y direction we have this expression. Here we also added magnetic field from Earth, BE. And now to find what is deviation, we just find what is a tangent of this angle. Tangent delta theta equal this relation. This is the answer for question A. For question B, assuming that KB and KS is very small, we can see that this tangent will be maximum when sine multiplied by cosine has maximum. And this happens for such angles like 45 degrees, 135 degrees, 225 degrees and 315 degrees. That's the answer for question B. A pair of iron balls placed in the same horizontal plane as a compass but a distance d away can be used to help correct for the error caused by the induced magnetism of the ship. Just like the ship, the iron balls will become magnetic because of the Earth's field BE. As spheres, the balls will individually act like dipoles. A dipole can be thought of as the field produced by two magnetic monopoles of a strength plus minus m at two different points. The magnetic field of a single pole is B equal plus minus m multiplied by vector r divided by r square, where the positive sign is for a north pole and the negative for a south pole. The dipole magnetic field is the sum of the two fields. A north pole at y equal positive a over 2 and the south pole at y equal -a/2, where the y-axis is horizontal and pointing north. A is a small distance, much smaller than the radius of the iron balls. In general, A equal Ki multiplied by Be, where Ki is a constant that depends on the size of the iron sphere. On the picture, a binnacle protecting the ship's compass in the center with the two soft iron spheres to help correct for errors in the compass heading. The use of the spheres was suggested by Lord Kelvin. Questions. Question C. Derive an expression for the magnetic field Bi from the iron a distance d much greater than a from the center of the ball. Note that there will be a component directed radially away from the ball and the component directed tangent to a circle of radius d around the ball, so using polar coordinates is recommended. Question D. If placed directly to the right and left of the ship compass, the iron balls can be located at a distance d to cancel out the error in the magnetic heading for any angles where delta theta is largest. Assuming that this is done, find the resulting expression for the combined deviation delta theta due to the ship and the balls for the magnetic heading for all angles theta. Solution for question C. Consider this picture, and on this picture let's check colored triangle with the black, red and green sides. The length of black side is A, angle between green side and the black side is phi. Red side will have length A sine phi, and the green side has length A cosine phi. Magnetic field strength from one magnetic pole a distance d away is given by this formula. The sum of the two fields has two components. The angular component is a measure of the opening of the triangle formed by the two vectors, and since the two vectors basically have the same length, we can use similar triangles to conclude that A sine phi over d approximately equal B in direction phi divided by B. And finally we have B phi equal this expression or this expression, and the radial component equal to this expression, and after calculations approximate value is this one, where x equal A cosine phi. And finally we have radial component equal this expression. And this is the answer for both radial and angular components for magnetic field. For question C. Answer for question D. Note that the two iron balls create a magnetic field near the compass that behaves like that of the ship as a whole. There is a component directed toward the ball given by this expression, and a component directed toward the starboard given by this expression, where the factor of 2 are because there are two balls. Note that theta is the ship heading, while phi is the angle between north and the location of the compass relative to one of the balls. Thus, if the field is corrected for the maximum angles, it will necessarily cancel out the induced ship field for all of the angles, so that delta theta equals 0 for all theta. Effectively, this means placing the balls to make KB equal KS. That was a solution for question T, and we answered for all questions for problem A3.